everyone, and welcome to the Frontiers of Parameterized Complexity. I'm very happy to introduce our speaker, Hans Bodlaender, who will be speaking on typical sequences revisited. Please, Hans, welcome.
Thank you very much, and thank you for letting me speak here. So this is joint work with Lars Jaffke and Arne Telle. Okay, so I'll tell you a little bit a story, and as some people know, I just turned 60, so I'm now an old man who actually also tells stories about the past. I still hope that you find part of this story interesting, but there's also quite some new things. But before that, we have to understand some old things like what are typical sequences. And then there is something which we found when we discovered it, a surprising lemma, which is called the merge dominating data lemma. This actually has some consequences, but one of them is it gives a polynomial time algorithm for computing Cutwidth on directed zero spell graphs. And I'll tell you that at the end. And at the very end, there is the open problem. So, but I'll start first talking about Treewidth and Pathwidth, and many of you will know these things, but then just stay here and wait till things come, which you may not know yet. So Treewidth is a graph parameter, and it was invented something like half a century ago, and the terminology which we now use is Treewidth, from the graph miner theory of Roberts and Seymour, but before that it was reinvented in at least a dozen different names. And it plays a role in over 20,000 papers, so many graph algorithmic theory, but also fixed parameter tractability, but also papers on different types of applications. And a lot of this talk, I'll talk actually about Pathwidth, basically because some things are easier to explain using Pathwidth, and they are just generalizing with a few extra technicalities to Treewidth. And for many of these applications of Treewidth and Pathwidth, it's important to be able to compute these values. So I'm giving a graph and I want to know what is the Treewidth or what is the Pathwidth. For Treewidth, it's actually already known a long time that it's NP hard, and there's also, assuming the small set expansion conjecture, there is not a polynomial time constant approximation algorithm. There are actually in a number of very practical algorithms. So for instance, for Treewidth 1, 2, 3, and 4, you can just compute the Treewidth in linear time, and this goes very fast. There is the work by Tamaki, which for relatively small graphs give you a practical algorithm. It is exact, but it is exponential. So if the Treewidth and the number of vertices grow, then the algorithm running time also grows. In theory, the fastest known FPT algorithm is this algorithm from 1996, and I'll give a lot of details about that later in the talk. And there's also a 5 approximation algorithm where the running time is as a function of the Treewidth only single exponential, and it's linear in the number of vertices. So let's look at this quote unquote fastest FPT algorithm for Treewidth. So in practice, it's very slow. It has been implemented, but even for Treewidth 3 and 4, this is very slow. And the constant factor is 2 to the something which is cubic in the Treewidth. But it's linear in the number of vertices. Now, even if you allow any polynomial, so not linear time, but quadratic or n to the 10 time, still this 2 to the order Treewidth to the 3rd is the best known already for now something like almost a quarter of a century. So this is a question which is intriguing. Is this really the best we can do, this 2 to the order Treewidth to the 3, or is there something better? And at this point, there is not really any lower bound known at all. Yeah, you can of course, prove a lower bound by just following the steps in the completeness proof that would give you something which is 1 divided by a polynomial in a tree with lower bound, but it's far away from what you want. And even something like 2 to the order Treewidth as a lower bound is not known at this point. So there is really a big gap between upper and lower bound if we look at the complexity of Treewidth as a function of the parameter Treewidth itself. And for Pathwidth, the situation is quite similar. The only difference is that this 3 becomes a 2 here. So there's a 2 to the order Pathwidth squared n-time algorithm. And you can also look at a recent paper by Führer where he also shows this. So, and it's still the best. Also here, again, it's the best known, and we don't have a good lower bound as well. So the question is, can we either find an FPT algorithm for Treewidth or Pathwidth whose running time is faster as a function of Treewidth or Pathwidth, or can we give a lower bound? And with our team, we were working on it, and at some point we tried to come up with gadgets, but to make lower bounds, and then something didn't work to make these gadgets, and then we had a conjecture, and then after some time later, this conjecture became a lemma, and I'll tell you about this lemma, and you also see then a corollary of the lemma at the end of the talk. So many of you will know this, but I'll still anyhow will tell you what is a Treewidth and what is a tree decomposition. So to define Treewidth, we need tree decompositions, and what we have is we associate a structure to a graph where we have a tree, and for every vertex of the tree, there is a set of vertices, which we call bag of that node. And there are 2 conditions. Basically, for every edge, there should be a set containing both endpoints. Like here, you see, for instance, for G and F are together in one of the sets. So for every edge, at least one of the sets contains both endpoints of the edge. And the other condition which you have to have is that for every vertex, all the bags that contain that vertex should form a connected subtree. Like here for the vertex C, it is connected a subtree here. Now, a graph can have many tree decompositions. For instance, this purple thing at the right corner is a tree decomposition where we have just one bag with all vertices. But what we want is that these bags are small, because if you use a tree decomposition, the running time is exponential in the size of these bags. So we define the width of a tree decomposition as the maximum size of a bag. And then for historic reasons, we subtract 1 from that. So in this case, we see a tree decomposition of width 2, the green one has width 2, and the purple one is a tree decomposition of width 7, and the Treewidth is just the minimum width over all possible tree decompositions of the graph. Now, practical algorithms or any algorithms using tree decomposition in general have the following shape: that for every node in the tree decomposition, I compute some information, typically a table of things. And to compute a table, you need the tables of the children, and then you go bottom up, and if you have the table of the root node, then you derive the answer which you want to have. So, and the table sizes are typically exponential size in the size of the bags, so in the size of the Treewidth. To make these dynamic programming algorithms easier to describe, Tolle and Kloks introduced in 1990 a notion which is called nice tree decompositions. And so it helps you to give easier descriptions of dynamic programming algorithms using these tree decompositions. And in a nice tree decomposition, the tree is rooted, and we have basically 4 types of nodes: a leaf, a join, introduce, and forget. And you can also show there's always a nice tree decomposition with the same width, and you can find that basically in some polynomial in the width times the number of vertices time. So let me go through these. I go through this 4 times later. And what you can do is, if you have this nice tree decomposition, for every node in the tree decomposition, we would associate a subgraph of your original graph. And the subgraph is basically the bag itself and all the vertices in bags below it, and then the graph induced by these vertices. So you can basically see we have a subgraph, and the bag is a separator which separates the other vertices of the subgraph from the rest of the graph. And this means that this is what is exploited in dynamic programming, that the vertices in the bag are, you need only to know some information there, and you have to have relatively little information about the part below. So we have this kind of separator property again. You can, for instance, now here, if you have 2 vertices, V and W, at different parts of your tree decomposition separated by the bag we are looking at, then if they're not neither in this bag I, then there cannot be adjacent. And this follows from the definition of a tree decomposition. So this means it's a separator, and this is precisely what is exploited when we do dynamic programming. So a leaf node is just gives me is a vertex with is a leaf where we have 1 vertex, and the associated graph is just the graph with 1 vertex. Now a join node is for a join node we have 2 children, and what we have is that all 3 sets are the same. And then a join, the graph you associate with the join node is basically obtained by doing this glue operation, where we identify the vertices in the 2 bags, and then we glue them upon each other. So I think the picture is probably quite clear here. For an introduce, we have 1 new vertex, which can only be adjacent to the vertices in the join. So there's a new vertex which somehow goes to this boundary of the current graph we are looking at. And you will see in the picture how this works. And in the forget node, we have the same graph, but 1 vertex now is no longer a graph in the boundary, so it becomes a normal vertex. And basically, another way of defining Treewidth is saying, okay, these are graphs you can build with these 4 types of operations. So we have a graph with, and here we have a little example where to see how you can actually also see this way. So this graph is Treewidth 2 because we can take a leaf node, we can introduce, so we have a vertex adjacent to the leaf, we introduce another vertex, we forget one, so this vertex becomes normal. We introduce a vertex, we forget the vertex, and in the same way you can make the other graph, and now you can do a join of these, and we have here this 6 cycle. And because we never worked with boundaries with more than 3 vertices, the largest boundary size is 3, so the Treewidth is 3 minus 1 is 2. And we forget, and we have the graph. So this is my first introduction, and I think for many of you probably will have known everything here. What I now will do is still something which is old, but useful for the third part. What I want to do is give some of the basic ideas of the FPT algorithm for Treewidth, but instead I'll use Pathwidth as running example. For Treewidth, the technique is more or less simple, but there are some additional technicalities, and if you want to read more of it, there is a really nice survey by Michal Filipczuk in a recent LNCS volume. So actually I will simplify some of these things, and some of the, so that the algorithm I present is somewhat slower, but asymptotically still equally fast as the best you can get. So there are basically, if you want to have this algorithm, there are 2 ingredients. One is an algorithm, which is basically a dynamic programming algorithm for Treewidth itself. This algorithm has as input 2 things, the graph itself and a tree decomposition of some constant width, L. but L may not be the optimal width, but it's still constant. And in the way it's used here, L is basically 2 times K. And then the algorithm decides whether the tree width or path width is most K, and if so, it gives you also a tree decomposition or path decomposition of the same width. And then this is the first ingredient, and the second ingredient is that there is a recursive algorithm which calls this first algorithm as a subroutine. And this second ingredient, the recursive algorithm, depends on a lemma, and I'll give you a weaker form of the original lemma. It's for path width, and the numbers are larger actually, but it helps really to show how the idea is going. So the lemma is the following: if I have a connected graph, I set some constant c, so you can see the formula there. And then at least one of the 3 things holds. Either the path width is larger than K, or I have a matching with at least n divided by 2 c edges, and which means that every maximal matching has at least n divided by 4 c edges, or I have n divided by 2 c pairs of twins of degree at most 2k plus 2. So a twin, you probably know what is a twin, but there are just 2 vertices which have the same set of neighbors. So these are twins. So what we have is either every maximal matching has many edges, or I have many twin pairs, or the path width is larger than K. So this is how the algorithm works. Will work, but I'll will give you a short proof of this lemma. So what I'm going to do is I have a path decomposition, and I assume that the path width is at most K. So I take a path decomposition of width at most K, and I split it in parts, in n divided by c parts, and every part should contain at least c vertices, and I can do that. Now I look at one part, I say, okay, the left bag and the right bag, the vertices there I call border vertices, and all the vertices which are not in the left and the right bag, but in the part, I call inside vertices. Now, so because these bags have size at most k plus 1, I have at most 2k plus 2 border vertices, and then c minus 2k minus 2, which equals 2 to the power 2k plus 2 inside vertices. So now if you use the notion of tree decomposition, inside vertices cannot be adjacent to vertices which are in a different part, because if they would have been adjacent to vertices in a different part, they should have been in the bags at the border, and they're not. So the only neighbors there are the vertices in the part itself. So now what we can have is one of 2 cases. Either I have 2 inside vertices which are adjacent. In that case, I know that inside this part there is an edge in a matching which does not involve vertices from another part. So I can just count one edge in the matching for that part. Or the other case, if this doesn't happen, then all the inside vertices are adjacent to only outside vertices. But then just a simple counting tells me that there must be 2 inside vertices which have the same neighborhood. And then, so we have a pair of twins, and that shows the lemma. So now we can make this algorithm in the following way. We basically follow the steps from the theorem. We first find the maximal matching. And if this maximal matching has this size n divided by 2c, what I'm going to do is I'm building a new graph by contracting all the edges in the matching. So I have now a smaller graph, and I go in recursively use the same algorithm to solve path widths on this smaller graph. Now, if this algorithm tells me that this smaller graph G prime has path width more than k, then also the path width of the graph itself is larger than k, and so the answer is no. Otherwise, I get a path decomposition of this smaller graph, and I can turn it in a path decomposition of the larger graph of width at most 2k plus 1. And then I solved the problem on this larger graph with the dynamic programming algorithm. I have a little example here. So you can see on the top the graph, and the edges which are thicker are a maximal matching in this graph. So if I contract this maximal matching, I get the second graph there. Then the third line, we see a path decomposition of that contracted graph. And now what we can do is for every vertex which is contracted, we replace its occurrence in every bag by the vertices that were contracted to it. And I get now a new path decomposition where the bags have size at most twice the size of the, so this is 2k plus 1. And now on this path decomposition, we can use this dynamic programming algorithm and solve the problem itself. So we use this algorithm, which gives me as input a tree decomposition or path decomposition of width, basically twice the value we want to have, and it tells me whether it has width. There is one with width at most k, and if so, it also gives the optimal path decomposition. So this is how the algorithm works. The second step is more or less the same. If we have many twins, then we basically identify each pairs of twins, and then we do basically follow the precise same steps. If the pathwidth of this smaller graph is larger than k, then the pathwidth of the original graph is k. Otherwise, in a similar way, we can turn the path decomposition of the smaller graph into one of the larger graph with twice width, and solve then the problem on this on the original graph with the dynamic programming algorithm. And if no sufficient large matching or sufficiently many twins exist, we say no, because the lemma tells us that tree width, path width is at most is larger than k. Now the running time is basically we go one single recursion with a graph which loses one divided by 2 cn vertices. So we get this running time, which is this line here. And if you look up how this goes in your first year algorithms class, then you can see that the running time is basically determined by the maximum of this value of c and the function of pathwidth of the dynamic programming. Now, see in our example, in my lemma, as I showed it, c is 2 to the order k, but actually you can get even a proof of a similar type of lemma where we have every time we lose one in order k to the third fraction of the vertices. So, and this was proven by Perkovic and Reed that you can get this cubic, only cubic error. Now, so then what really is the dominating time is this function of the pathwidth or tree width for the dynamic programming algorithm. And the best known for pathwidth of this dynamic programming algorithm is 2 to the order k squared, and the best known for tree width is 2 to the order k to the 3. So if we want to improve there, we have to, this recursive scheme is fine. We cannot really gain a lot there. We really, if we want to improve this algorithm, a thing to focus on is on this dynamic programming algorithm. So what we have as input is a tree or a path decomposition, and as output we want to know the optimal value of the tree width or path width, and if so, you want to also find the corresponding path or tree decomposition. Now, the latter step, if you allow more than linear time, you could also solve by using a self-reduction scheme. So the decision problem really is the limiting factor if you want to look here. So this is the question, what I'm going to look at. If given is a tree decomposition of width at most L, integer k, and I want to say no if the path is larger than k, and otherwise a path decomposition of width at most k if existing. And in the same iCalp in 1993, Tom Kloks and I had a paper there, and Stefan Arnborg and Jens Lagergren also had the paper, and we basically proved the same result there with a small changes in terminology and also in some details. So Jens and Arne and Stefan showed that you can had results about the number of forbidden minors of Treewidth and Pathwidth, and we looked at constructive variations there. So the time for Pathwidth is 2 to the order k times L, and for Treewidth it's 2 to the order k squared times L. And the basic idea of these algorithms is that we, for every node in the tree decomposition, we're going to compute a table, and every table entry is the fingerprint of some path decomposition of this associated graphs. And then the number of fingerprints is 2 to the order KL. And then for join, introduce, and forget nodes, you can actually compute these tables in order 2 to the KL time. And the leaf table also is, that's basically trivial. So we really have to understand here, to understand the algorithm, what is the fingerprint of a path decomposition. And the fingerprint basically consists of 2 parts, 2 aspects. The first thing is that we are going to split the path decomposition in parts, and every part has the same, if you're in the same part, you have the same intersection with the vertices in the bag. So if we have a bag, say VW, then, and this is my path decomposition of this subgraph in, for associated with I, then we have 4 parts. The first part are the bags where the intersection is V. The second part is the intersection VW. The third part is the intersection W. And the last part are those which have an empty intersection. So in this way, we split this into parts and we get this intersection model as below. Now for every part of the intersection point model, actually, it is not important anymore to know the names of vertices in these bags, because all the vertices which still can be adjacent to vertices which are not yet in this subgraph, they are already determined by the intersection model, and all the others are forgotten and they will not get new neighbors. So we can just write down the sequence of bag sizes. This is not yet sufficient to get the fast enough and FPT algorithm, because we can have large sequences of many bag sizes. But actually what we are going to do is we can replace the sequence by the typical sequence. And I'll define next what is the typical sequence. So, but before to define the typical sequence, I need to introduce a few notions here. The first notion is just the extension of a sequence of integers. And an extension is just, I take the sequence and every number in the sequence can be repeated 1 or more times. So for instance, if we have the sequence 55714, we might determine to repeat 7 for a number of times, and we might repeat other numbers more than once or not. Now we say that an integer sequence dominates another integer sequence if we have extensions of equal length, such that for every position, the first one is smaller or equal than the second one. So now what is the idea here? The idea is that if I have a path decomposition and all the numbers are the sizes of bags, then I can basically repeat a bag, and repeating a bag means that in my sequence, I have this size once more. And if you just repeat a bag, it's still a path decomposition, fulfills all the properties. So this is the way of this extension, the idea about extension. And then this domination means that if I have that the sizes are at most the sizes of the other one, well, a smaller bag is always better. So basically the idea is that if one sequence dominates the other sequence, then any method how you extend the first one, any method where you extend the one which is dominated can also be used to extend the one which is the dominator, and then you still have a solution. So this is more or less the intuition there. So if you have two sequences and one dominates the other, you basically can forget the second. So if we have two interval models which are the same, but for every part the sequence is dominated from one by the other, then the one where everything is dominated can basically be removed from our table, and we still have a valid dynamic programming algorithm. So that's the idea. And now the interesting thing is that you can characterize this more precisely by a notion which is called, which Ton and I called typical sequence, and was introduced simultaneously by Lagergren and Arnborg in 1991. And the operation of a typical sequence is the following. If I have a subsequence of numbers where the first one is the smallest and the last one of the subsequence is the largest of the subsequence, or vice versa, the first one is the largest and the last one is the smallest, I remove all the middle ones. And also will, if I have two numbers which are equal to each other, next to each other, I remove one of them. So if you have, for instance, this typical sequence here, then 2, 4, 9, 3, 3, 4, 5. Well, the 4 is in between 2 and 9, so it can be deleted. And then 3, 3, 4, 5, basically the 3 and 4 are between 3 and 5, so they can also be deleted, and I get this typical sequence. Now, typical sequences have a very special shape. There is in the middle, or say somewhere which we might call the middle, there is the maximum or the minimum. And then at the other sides, we have this oscillating sequence where we go to a small value, a large value, a small value, a large value, and every time the larger values are getting smaller and the smallest values are getting larger. So they always have this type of form. Now, we can also introduce a notion of equivalence when we say that two sequences are equivalent when they dominate each other. And then you can actually see that a sequence dominates another sequence if and only if the typical sequence dominates it. They are actually equivalent if they have the same typical sequence. And you can also show that the number of typical sequences of integers between 1 and k is single exponential in k. And this is nice because we can, for every part of my intersection model, we don't need to write down the back sizes, but we just write down the typical sequence of the back sizes. And this precisely captures all the information that I need for the dynamic programming. So this is how these dynamic programming algorithms, both the one by Ton and me and the one by Stefan Arnborg and Jens Lagergren work. What we have is we have for every node in the tree decomposition, I write down the collection of all possible typical sequences of path decompositions or tree decomposition of width at most k. For the intersection model, plus for every part, you take this typical sequence. Now for Treewidth, it's very similar, except that you have in your tree decomposition still some parts which you first throw away, and then you have some trunk of the tree, and the tree itself is again can be split into something like L square different parts, and then this is more or less how you can, and for each part again you have a typical sequence. So you can, the algorithm would work as follows. For every of the nodes in the tree decompositions, I will compute this table of fingerprints, and I have subroutines for introduce, join, forget, and leave nodes for computing these tables. And actually, you don't need to compute all, but you can actually limit yourself to two fingerprints which are dominating. Because if a fingerprint is dominated by another one, you know that you don't need it. for getting the optimal answer. Now, in the join node, we need an operation to compute these values. We need an operation which is called the merge. And let's look what happens in one of these pieces. Then we have two integer sequences, and what we can do, we want to know. So if we have a path decomposition of the one part, and we have a path decomposition of the other part, and these are somehow merged together. Now how do you merge together? You take vertices on the first bag and the second bag, join them. You might copy a bag and join the vertices there, and so on. So what you do is you take extensions of the same length, where if you copy a number, you copy the bag, and then you add these numbers coordinate-wise, which means that you take the union of these bags there. And actually, you know the intersection of these sets, because these are precisely, the intersection is precisely determined by the intersection model. So basically what we do here, what happens in practice is you have this sequence of integers, and you take an extension and you add them coordinate-wise. So you could, for instance, merge 3, 1, 5, 4 into 6 to 5. You add the 3 and the 2. You maybe make copying the 2. You have then that 3 is, but you take the next one here. So it's 3 is 1 plus 2. You still copy the 2. So you have 7, which is 5 plus 2. But now you might copy the 5. So you have 5 plus 6 is 11, and then you would copy the 6 again, and you have 4 plus 6. So that is one way of a merge, but you can see that two sequences have a large number of different merges possible. And this is what happens in the join. We basically split first our tables in those parts which have the same intersection model, and for every intersection model we take all typical sequences of all the merges of the typical sequences in these subparts. Now, the original algorithm takes the typical sequences of all the merges, but actually we only need to take merges that are not dominated by another merge. So we need to only take merges which are dominating merges. And while we are trying to construct lower bounds, we asked, well, if we have two of these typical sequences, how many dominating merges are there actually? And we try to come up with examples with many dominating merges. So this was actually done while Arne was on sabbatical, and while we were having a break, we walked through this really nice street there in Valencia. But that's why there is a nice picture. So, but after that, we started thinking again, and we didn't come up with good examples of large sets of dominating merges. And then we had this conjecture, and then the conjecture became what we call the merge dominating lemma, which tells me if I have two integer sequences, and I have the set of all the typical sequences of all the merges of these integer sequences. So basically, every element in these A and B are repeated one or more times to get sequence of equal length, and then add them coordinate-wise. And then this lemma tells me that this set has a unique element which dominates all the elements of C, a unique typical sequence which dominates all of them. And you can actually find this also, the proof is constructive, and it gives you a linear time algorithm actually to find this dominating merge. Now, so if you have the sequence, for instance, these sequences, they have as merges a lot of different merges, and there's one which is dominating, which you can see here. Yeah. Now, I'll just do a brief sketch of the proof of the merge dominating lemma without going to deep details. How are we going to prove this? Well, first of all, what you can observe, it's actually such a merge is you can write it all, see this as a path in a graph, and actually a very special graph, namely it's a graph in a grid. The graph is a grid. So what we are going to do is we take a matrix and we label the rows with the numbers from the first sequence, and we label the column, and the columns we label with numbers from the second sequence, and every value in the matrix is just the sum of these values. And you can see that here, this matrix here is obtained in this way. And now a merge, what you always have to do is you have to start to add the first element of the first sequence and the second element of the second sequence. And then you might either copy one of them, which means you go a step up or a step right, or you copy none of them, which means you go a step left up. So you either take the sum of the next element in the first sequence and the element you are working with in the second sequence, or first and second sequence reversed. So you can either, here if you go up, you copy the second sequence and you take the next element in the first sequence. If you go right, you copy the first sequence and you take the second element in the second sequence, and you go right up, you copy both. You copy none of them. You can also copy both of them, but that would mean repeating a value, and that doesn't do anything useful anyhow. So basically what we have is we have to find a path in this graph. Any merge is just a path in this graph going from the left lower left corner to the right upper corner of this matrix. And using that, you can actually prove and prove things and show this merge dominating lemma. And there are two proofs. Well, the proof is many pages long, so I'll just give a few hints here. So the first thing is that any typical sequence has a unique minimum or maximum, and for instance, if they both have a unique minimum, then the sum of these minima must be in the dominating merge. So if they have a unique maximum, it's again a little more technical. But if they have both a unique minimum, then we know that we have to add these sums here. And that means that we split. We can, after that, if we know that we have to add this one here and this one there, we basically know that after that we have two problems left. The left thing which happens on the left and the thing which happens on the right. So you take the dominating merge of what is left and you take the dominating merge of what is right, and you append them, and this gives me the final dominating merge. So that's the split part. And then there's the chop part, which means that we know that the minimum is at the first or the last position, and then there is some kind of clever case analysis which tells us what is the first step, and we use induction. And this is more or less how the algorithm goes. Now, the case analysis is actually not so very large. We know we have to add 1 and 1. So we know that at some point we have to either get the sum of 7 and 2, the second element of the first and the third element of the second, or the third element of the first and the second element of the second. We look of which of these sums is the largest, and the one which is the largest we get away from, we basically resolve. And so we chop the 1, 7 part, because we don't want to get this 9. So we basically put the 7 instead of with a 2, we are going to put it together with a 1. Which means that I start with adding 1 to 1 and then adding 1 to 7, chopping that, and then we have the start of our sequence here, and then we basically throw away that part, and then we append the dominating merge of what is left after that. So, and in this way you continue. So this is this dominating merge lemma. What does this mean? Well, for the dynamic programming algorithm for Treewidth, it means that the join step you can actually speed up significantly, because there is for the join you have to look. We thought we had to look to all the different ways of merging two sequences, but instead there's only one of them. So what you can do is you look at every pair and put in the new table only the dominating one, instead of putting in the table all the different merges. Unfortunately, it does not improve the asymptotic running time yet, because basically at this point, the blow up comes from the introduce and the forget nodes. In particular, the blow up is generated by introduce nodes. And you still get for all these algorithms, as far as all we see for about always, you get the same asymptotic running times. It also shows that some of the tricks you might want to use for building lower bound gadgets may not work. For instance, if you want to say, okay, I built something else, and then I do a join there, well, that might not really give a lot of ways to play, because this join basically has a unique best way of joining things. But also it gives some interesting corollaries for very special cases. And I'll end my talk with giving one there, namely I'll look at the Cutwidth of directed series parallel graphs. So the theorem is the following. The Cutwidth problem can be solved in quadratic time for directed series parallel graphs. And while this is frontiers of parameterized algorithms, this is just a polynomial time algorithm. So the only parameter is just that series parallel graphs are graphs of Treewidth 2 directed, but that's it. But still, this algorithm is found by just using techniques which come from the FPT world. So what is a directed series parallel graph? Well, it's a graph you can build with a number of operations. The first is just I take a single edge, directed edge, then and every directed serial parallel graph has two special vertices, a source and a sink, S and T. And what we can do is, if we build this graph by taking smaller series parallel graphs and doing either a parallel or a series composition. And the picture is probably quite clear. If you have a parallel composition, you identify the sources and you identify the sinks, and you get a new SP directed series parallel graph. And in a series composition, you identify the sink of the first with the source of the second, and you basically forget. And then the new terminals are the source of the first and the sink of the second. You can see it in the picture. So this vertex is the new source, and this vertex is the new sink. The vertices of degree 0 and in degree and out degree 0 are the source and sink. And these directed series parallel graphs have been invented, I think, before I was born. So they are, and they play, for instance, a role in electrical networks and very old graph algorithmic studies. So there is acyclic. There are a directed variant of series parallel graphs. If you forget the directions, then you have a graph of Treewidth 2, but they can have arbitrary large cutwidth. Here's an example where the cutwidth is large, but I'll still have to define cutwidth, which I'll do next. So cutwidth is the following. You can define cutwidth for undirected graphs, but for directed acyclic graphs, you define it as follows. We want to find a topological sort of the graph, so an ordering of the vertices such that all arrows going from left to right. And then the cutwidth is the number of edges you can cut if you look between two vertices. Well, here in the right corner, you see the mathematical formula, but the picture is probably more clear. At every point between two vertices, you see how many edges you cut if you go there. So how many edges have a left point left of it, and the other endpoint right of this cut. And now the cut width is just the maximum over all these cuts. So in this case, we have cuts of 2 and 3. So the maximum is 3. So this is a layout or topological sort of cut width 3. And the problem is find such an ordering, a topological sort where this cut width is as small as possible. Now, for arbitrary directed acyclic graphs, this problem is NP complete, but for directed for series parallel graphs, we have a quadratic algorithm. And the algorithm is basically the following form. We just take the known algorithm for cut width, the FPT algorithm for cut width, for undirected cut width. This was, I think, classic work for a long time. You take, I think it's together with Dimitrios worked on that. So you take a dynamic programming algorithm for Treewidth. Well, that uses, if you look at it, the cut width to the order Treewidth, some function of the cut width and time. Now you can use the same algorithm for directed cut width by just only taking elements in your tables which respect directions. You get with the same running time an FPT algorithm for cut width parameterized by Treewidth. But now, in this case, we just take one additional modification. We only take the dominating typical sequences. And then if we analyze what happens, there's just one entry per table. So every table, our algorithm is no longer a real dynamic programming algorithm with a whole table of different things. Every table just has one dominating entry. And then if you look and analyze what happens, well, the running time to find this next entry is basically order the cut width, because this is the typical sequences are of size order cut width, and then you get an order cut width times n or n square algorithm. So that's a polynomial time algorithm. So how does the DP algorithm for the cut width look like? It's quite similar to Pathwidth. What we are going to do is we have divide our sequence in parts where every part is separated by a vertex in the back. So if we have, for instance, vertices V and W are our bag, then we have 3 parts, everything before V, everything between V and W, and everything after W. And for each of these parts, you look at the sizes of the cuts, and then for these sequence of sizes of cuts, you take the typical sequence. And this is the fingerprint. And this DP algorithm for cut width, parameterized by Pathwidth or Treewidth, is just tabulating all the possible fingerprints of this type. Now, if you have a directed series parallel graph, this becomes a little easier because the first vertex S and the last vertex T, these boundary vertices, have to be the first and the last vertex in the sequence, because I have these are the only vertices with in degree 0 or out degree 0. So my typical sequence will be, my model will be just consisting of S, then one typical sequence, and then T. Or you can, and then you can basically forget S and T. So my model is just one typical sequence. And then you can see that there is actually, by induction, you see that there's only one dominating fingerprint. And you can find it in linear time. And we have just to do induction to the different operations to build directed series parallel graphs. So the base case is trivial. We have just a cut of 1 and the typical sequence is size 1. For series, well, this join of 2 series, what you do is you can just take the first typical sequence, append the second typical sequence, and then after that, you just take the typical sequence of when you append these. And you can show, and it's not hard to see, that this is actually the dominating typical sequence of this series composition. Now for parallel, there we are going to use our lemma, because the original, well, basically what we have is we have two typical sequences, and you can see that actually any solution which you have is if you have a set of, the top part has a sequence of vertices, the lower part has a sequence of vertices, and somehow these are merged, like in a merge sort step together. And what happens to the sizes of the bags is basically, this is precisely a merge of these numbers. The sizes of the cuts are just the merge as we defined it yet. So we don't need to take all merges, we only need to take this unique dominating merge. And this dominator merge lemma tells us that there is only basically one solution, one way of merging these sequences, which gives us a guaranteed best solution for anything you want to do later with it. So this is what the algorithm is doing, taking these sequences and then take the unique dominating merge. And that's it. So we find this dominating fingerprints for every subgraph following the way the series paragraph is constructed. And the minimum Cutwidth in the end is the largest integer in the typical sequence of the graph G itself. And this is, and you can also make this constructive by and show that the algorithm also builds the corresponding topological sort. And this was already known for many decades, that actually an expression which builds the SP graph with series and parallel compositions, you can find that in linear time. The same technique works also for a variation of the problem, which is called directed modified cutwidth, where we don't cut between vertices, but actually you look at the cuts at vertices. So for every vertex, you look at how many edges go from left of that vertex to right of that vertex. And the same technique also shows that you can, this directed modified cutwidth can also solve in quadratic time on directed sequence paragraphs. So that was more or less all what I wanted to tell you. So we had this, we found this dominating merge dominator lemma surprising in the sense that we didn't expect that to be the case, but in the end it happened that it was true. You can speed up with it the join step in algorithms for Treewidth and Pathwidth and several other width measure type, similar type of algorithms at the join nodes. But it doesn't give an asymptotic speed up, but because now the bottleneck actually is moved to the introduced nodes. And that gives me to the open problem. So I'm going to give you one open problem, and it's open now for a quarter of a century or more or less. That is, what is the parameterized complexity of Treewidth and Pathwidth as a function of the parameter itself of K of Pathwidth Treewidth? And the lower bound, this problem can be attacked at two sides. First of all, we might want to have any lower bounds based on the exponential time hypothesis or the strong exponential time hypothesis. I would already be happy with any lower bound, which is basically 2 to the order K. That would already be something. And then the upper bound. So we have for Pathwidth something which is exponential in K square. For Treewidth, we have something exponential in K to the 3. Can we get something faster? And don't worry about the linear time. I mean, even something with cubic, any upper bound where we don't have a linear time algorithm, but a polynomial in N is that there. So I think this is an intriguing open problem, and I hope that maybe some of you can make some progress there. Well, thanks a lot for listening to me. And if you have questions, I would be very happy to hear them.
Thank you very much, Hans, also for entertaining us. Yes, there are some questions in the chat.
I see one in the chat here from Mika. Concerning the optimality of the DP routine, consider a vertex set B of size order k in graph G and the family of 3 decompositions of width must k. How large can this be? So, yeah, so this is a really good question. What we can basically show. So the question is how many non-equivalent fingerprints can there be of 3 decompositions of width plus k? We can, yeah. So yeah, you can get 2 to the omega k square. So basically, what we have is, because that's the number of intersection models. So you can actually, for every intersection model, you can that. So for Treewidth, you have basically 2 to the order k square intersection models, and you can show for it. You can give all different types of intersection models, but then the last k comes from the number of typical sequences, and then I have no way of getting more than one there. So that's more or less the difference. Yeah, is that a clear answer? And for Pathwidth, you can basically have a similar thing where the k square is a k. You can have 2 to the order k omega k intersection models, different path decompositions. But then still, I have only one, and then that's where I also, one of the things where we got stuck is getting more typical sequences there. I don't know. What about undirected graphs? So I don't know. For undirected graphs, these vertices S and T don't need to be at the front and at the end of the decomposition. So you could if you have this linear ordering, you could have this vertices S and T somewhere in the middle, and then my typical sequence is split into 3 parts: something before S, something between S and T, and something after T. And then by different steps, you can actually still blow up the number of typical sequences. So it's not clear that you get to the polynomial time algorithm there. I see 2 questions in the chat. Are there other questions?
Oh, then maybe just thank you once again, Hans. Yes, have a nice holidays then. And see you.
Thank you for listening.
Bye.
See you again. Bye.